Okay, let me try to record the lecture note for December 1. We will finish nuclear synthesis and then discuss a little bit about the inflation today, if I can. Okay. So we have been talking about the generation of heavier nuclei, and let's talk about the beyond deuterium. So we are interested in this ratio of ND over NN, and as the universe cools down, this does not remain indefinitely at the equilibrium, so equilibrium breaks. For example, deuteron can fuse into a proton to form helium-3, and one example is deuteron plus proton can be fused to helium-3 plus some energy release in terms of gamma. Or you could produce what's called tritium, which is you have two neutrons and one proton combined together. So that can be formed from deuteron plus neutron with gamma energy release. But this tritium is unstable, and it's a weak decay with the mean time of 18 years. But in terms of Big Bang nuclear synthesis, it's practically infinite. On the other hand, another possible fusion, including generating helium-4, is basically two deuteron making helium-4, or even with higher probability, you have two deuteron making tritium plus proton, or helium-3 plus neutron, and so on. And once that happens, we initiate reactions like helium-3, tritium plus proton, making helium-4, helium-3 plus neutron making helium-4, and deuteron plus tritium making helium-4, or finally helium-3 plus deuteron making helium-4 plus proton. These are, as you can see, all are strong interactions. And once helium-4 is reached, as I said, helium-4 is even nuclei, so binding energy is very strong. So the next fusion process will slow down. On the other hand, rarely helium-4 with deuteron making lithium-6, or helium-4 plus tritium making lithium-7, or helium-4 and helium-3 making beryllium-7 with all the gamma energy release. So all those things eventually happens, and once beyond a mass number greater than 7, you can think of helium-4, 2 of helium-4 making beryllium-8. But it has decay time of 10 to the minus 16 to back to 2 helium-4. So I introduced this picture in the beginning of the chapter 9. So it's again vertical abundance as a function of temperature or in time on the top horizontal axis. So all the things that we discussed is very qualitative statement, but if you are serious, you can write a program, computer program, to calculate these things systematically. So that's what we call standard Big Bang nuclear synthesis model, and that's the result. This picture is the result of such a massive computation. All right. Now let me conclude chapter 9 with discussing one thing which we call baryon-antivarion asymmetry. This is, to be precise, a particle physics problem, but let me discuss briefly anyway. So at the time, temperature of Big Bang nuclear synthesis, which is about very close to 10 to the 9 Kelvin, the energy density of nuc is this standard black body radiation stuff, that's 10 to the 33 MeV per cubic meter. So if you convert it into mass density, that's close to be 3,000 kilogram per cubic meter. That's about 3 times heavier than the water. What about the mass density of the baryon at that time? So if you use a benchmark model, the density of baryon at any given time, and here we are talking about time at nuke, is the baryon omega baryon as of today times critical density, and you scale up to baryon time. That's basically time reverse of time ratio power of 3, and it turns out to be 0.01 kilogram per cubic meter. That's very small compared with the radiation. So at BBN, with the baryon to photon ratio of 6 times 10 to the minus 10, and antibaryon was very smallest, and baryon is there, and radiation is dominant. But before BBN, we expect that there's a quarks floating around freely, and once you have it, 2 photons annihilate quark and anti-quark pair. So you expect amount of matter, or amount of number of quarks and number of anti-quarks, they should be similar because of this reaction. But at BBN, there's no antibaryon. We only saw helium, lithium, and so on. There's no anti-lithium, anti-helium. So that's strange. So if you construct this asymmetry parameter, which is the difference between number density of quark and anti-quark, normalized by sum of them, it's less than 1 because there is no anti-quark, but it's not 0. These two quantities are not exactly cancel to each other. Otherwise, we wouldn't exist because we are all matters only. So after annihilation of quark and anti-quark pair, as universe cools down, there's this delta should be non-zero, and it's now nq over n gamma, which is approximately delta q from this formula, to have eta to be very small. And the real question, this is particle physics question, so I don't really want to go into details. But the question is, where is this asymmetry coming from? Otherwise, as I said, we don't exist. So there's a mechanism to have such an asymmetry, which we call the Sakharov condition and so on in particle physics. But this class is cosmology, not the particle physics. So I'm just leave this question as is and move to the next chapter. So that's chapter 10 is kind of core of the entire semester. And we want to talk about very early universe, as early as 10 to the minus 35 seconds after the Big Bang. And there's a period called inflation. It's super accelerated period of the universe in very early universe. And why do we need it? That's what we want to discuss. Anyhow, so far what we have learned is called the standard Big Bang cosmology. And we have reason to believe that it has to be modified. So let me today briefly mention the flatness problem. So let's write Friedmann equation with the curvature term in it. So 1 minus omega at any given time consists of a curvature term with this stuff. And if you evaluate this equation as of today, you have 1 minus omega 0 equal to kappa, and Hubble parameter became Hubble constant, and scale factor is 1. Now this 1 minus omega 0 itself can be measured with a CMB and type 1 supernova stuff. And we saw that the absolute value of 1 minus omega 0 is less than percent level. So omega 0 itself is pretty close to 1. And if you can convert by using this equation, that means the radius of curvature should be greater than about more than 10 times c over h0, the Hubble distance. And the question that we are asking is, why is the omega close to 1? It can be 10 to the, it can be 100, it can be 0.01, it can be 10 to the 16, it can be 10 to the minus 16. There's no real constraint. So let's take a ratio of previous two questions, two equations, sorry. And then we have this formula, 1 minus omega consists of Hubble parameter and constant, and 1 minus omega 0 and scale factor square. Now, when we think about the time much less than matter and lambda dominant period, and that was, by the way, about 10 gigayear, and we only have radiation and matter, so Friedman equation became this. So you plug this h over h0 right there in to get rid of Hubble stuff. Then 1 minus omega t is consisting of this omega 0, r0, m0, and scale factor. So during the period of radiation dominant, you see that 1 minus omega at the radiation dominant era is proportional to a square from the previous equation, and that's proportional to t, because a is proportional to t power over 1/2. And in the matter dominant era, we still have a term that is related with time power over 2/3. So if you move all the way back from present to radiation matter equal era, you find that 1 minus omega rm is 10 to the minus 6. Now if you go back to the BBN time, where the scale factor is expected to be 10 to the minus 9-ish, then 1 minus omega nuc is 10 to the 16. Seems to be very strange. I'll explain in a minute. And if you are there to keep doing this all the way to the Planck time, 1 minus omega Planck is 10 to the minus 62. So what does it mean? In the beginning of the universe, omega value was really fine-tuned to 1 to the precision of 10 to the minus 16. If you don't believe Planck stuff, then BBN is something that we all are sure about. You have to precisely, not you, but the God or whoever makes the universe in the beginning, omega nuc has to be fine-tuned to be 1 down to 10 to the minus 15 to precision. Well, you can say that, okay, this is an initial condition. Somehow it was set. But that's not the real explanation. You have to explain why such a strange initial condition is met. In other words, what kind of physics was driving such a condition? So that's the inflation that we will discuss perhaps next time. I'll stop here today. Bye-bye.